Hello everyone, welcome to this online lecture on dielectric properties of insulators. This is a new module and this is the first lecture in this module. My plan in this module is to discuss the behavior of insulating materials, right? Usually the insulators are good dielectrics, and the word dielectrics arise because the die here means something that oppose electricity, right, or oppose electricities. That's where the name comes, right? So die means in this context some material that will oppose the flow of electricity, and those are really the insulators, right? Now usually when you want to characterize the electrical conductivity of some material, we always use the conductivity, right? That's you can measure in the lab. That's why the material is characterized in terms of the conductivity, and the unit of conductivity is 1 by ohm centimeter, right? And this is the inverse of the resistivity unit. The resistivity is usually denoted by sigma, and sigma is nothing but 1 by rho, right? And the resistivity of the unit of the resistivity is ohm centimeter. That's why for conductivity we use 1 by ohm centimeter. Now let me show you a spectrum where I'm plotting the range of the electrical conductivity of different materials, right? So let's say on the very far left end we have quartz, drywood, rubber, and then we have gallium arsenide, silicon, germanium, then we have like manganese, iron, like silver, copper, right? It's different materials, and you can see in this wide range the conductivity is varying from 10 to the power minus 20 to all the way to 10 to the power 6 in ohms, 1 by ohm per centimeter unit. Now usually this range of materials are known as the insulators or the dielectric materials. This here the semiconductors, and then we have the metals, right? And if you ask yourself that what's beyond these metals, right? So metals are really good conductors. Then beyond that we have the superconductors, right? And we have already discussed the superconductivity. And an estimate of conductivity for superconducting materials is 10 to the power 20 1 by ohm centimeters. And you can see that means that the conductivity span starts from the insulating, the very good insulators, where the conductivity is of the order of 10 to the power minus 20, and all the way up to a very right hand side, maybe way beyond there, we have some superconducting materials whose conductivity is 10 to the power 20, right? So you can see, if somebody asks you that for some materials, what is the span of the conductivity in units of this 1 by ohm centimeter, you would say that's 10 to the power 40, right? Starts from minus 22 all the way up to somewhere for the superconducting materials, right? So the best conductor are like the superconductors, and the insulators are the best insulators are somewhere in the very left end of the spectrum. So the span is like 10 to the power 40, right? And if that's like an enormous range, right? So the materials shows enormous range of conductivity depending on their structure, right? And that's why this is really a fascinating topic to understand why certain materials conducts well and certain materials really poor in conductivity. And this is a really fascinating subject in material science, right? And just to make a comparison, this kind of range, right, you can compare the diameter of the universe to the radius of the electron, right? So the diameter is like 10 to the power minus 26 meter, that's an approximation, and the radius of electron is somewhere 10 to the power minus 14 meter. So you can see it is as though we are comparing the universe diameter with a single electron radius. That's a huge range, right? That's what makes this subject really fascinating, this topic, that you will see every material, when people discover some new material, the first thing they do, they always measure the conductivity in the lab, right? Because that's really a way to the starting point to understand what sort of material. Is it a good conductive? Is it a metal? Is it an insulator? Is it a semiconductor? These are really a very important question to characterize materials, right? And the insulators has really poor conductivity, right? And the best ones are like the no electricity flows through them. And one question usually asks that, okay, so we have different materials and their conductivity is varying over a very wide range. Why is the case? You know, the electricity inside any material is carried by electrons. So a general question usually asks about the number of electrons, right? So is it the case that, okay, maybe for the insulators there are few electrons, and for like the metals there are a huge number of electrons? Is it this case? The answer is no. Every material has like the number of electrons. They have like equivalent number of electrons in every material, right? So this is really interesting. Then, although let's say quartz and ferrous, in 1 mole of quartz and 1 mole of ferrous, we have like Avogadro's number of, let's say, order of electrons. But this one doesn't conduct electricity at all, but this one conducts really well, right? So those things we already discussed in different topics, in different subjects, in terms of different physical phenomena, right? For example, if you recall that one good way to characterize these materials is the band gap, right? You can measure experimentally the band gap of different materials, and from the band theory we know that the materials, usually the band diagram consists of this Ek, right? We are plotting the energy in the y-axis, and the wave vector k is along the x-axis, right? And then it can, usually there are some low-lying bands. So these are like 2 bands in the below here, and there is 1 band in this figure. And the gap between, if there is a gap between, usually these are the valence band and this is the conduction band, right? So this is conduction band and this is your valence band. And usually conduction band and the valence band for insulating materials are separated by some gap, right? And this gap from the top of the valence band to the bottom of the conduction band, usually what is known as the band gap of the material, right? And insulating materials has wide band gap, right? A large amount of band gap. And I am showing these 2 pictures just to make a distinction that sometimes what happens for materials, the conduction band minima and the valence band maxima, you can see in this picture, they are kind of aligned in the same K value, right? So, but here it can happen that for some materials, the conduction band minima and the valence band maxima may be in different K points. So we are plotting K in this axis and energy in this axis. So usually these are indirect band gap materials and these are direct band gap materials. And I know you know already these things from your undergraduate semiconductor courses. So this is a direct band gap material and this is an indirect band gap material, right? Where the conduction band minima and the valence band maxima occurs at different values of K. So this is a K is equal to 0 and this is some value where K is really not equal to 0, right? And this is our indirect band gap material. And usually the insulator like silicon dioxide, right? They have very large band gap. The band gap, this is of the order of, let's say, 9 electron volt. And let's say we have quartz, right? So quartz is of the order of, let's say, 10 eV. So you can see these are really enormous band gap, and that's why they are really good insulators, and electrons hardly flow through them, right? So that's the defining properties of many insulators, that they have wide band gap, a large band gap. So we can say that insulators are characterized by this large band gap in their Ek diagram, right? So we have given some examples. Now, to understand the behavior of insulating materials, we need to review some of the basics from our electromagnetics courses. So in this lecture, the first lecture, my plan is to go through some of the very basics that we will be using in the lectures to come. So that's why I give this part of this discussion as a review on electromagnetics, right? The first thing that we want to discuss is that the electric dipole, the concept of electric dipole. Dipole means we have two poles, so plus and minus. So an electric dipole is formed when 2 point charges, right? So we have 2 point charges equal in magnitude but opposite in sign, right? That's the important thing. So that's like a dipole where we have some plus q charge here separated by some distance d, and there is a minus q. So that's a dipole configuration, and we are putting our origin of the coordinates in halfway between the charges, right? That's our origin. So the plus charge is along the z-axis, the distance is d by 2, and this is minus d by 2. So the total distance is d, and this is our electric dipole configuration, right? And if somebody asks you that due to this configuration of charges, what is the let's say we have some P, and we are asking what is the electric field, which is a vector, right? And this R is also a vector, and what is the electric field at some point R? And R, you can see the distance R is not really from the charges, rather from the origin of the coordinates, which is the halfway between the charges. So if somebody asks you what is the electric field at some point, that's the formula that you have already, I believe, discussed in your electromagnetics course somewhere in second year. And the electric field is given by 3 times many things. So let's put, usually in the text they make the vectors in bold letters, but to avoid confusion I want to put arrows everywhere where we are talking about some vectors, right? And you can see that we are making a dot product between 2 vectors. One is the distance vector, right? The r vector, the distance of the point from the halfway of the between the charges, that's r, and something that's p. The p is what is known as the electric dipole moment. Electric dipole moment, and this is defined, so this is the vector quantity is defined by the amount of charge that we have here, plus or separated plus and minus charges. So that's the amount of the magnitude of the charge and the distance. So distance is a vector here, so you can think of this vector as a vector which starts from minus q to plus q, right? So the d vectors has a direction from minus q to plus q, and that's our electric dipole moment. And in this equation we are taking the dot product of the dipole moment times the coordinate vector, so that's a scalar quantity, right? So but then this scalar product is multiplied with some vectors, that's a vector quantity, and this is the vector p, right? And r is square, right? So in this equation this r is nothing but the magnitude of the coordinate vector r, the position of the point p. And in the denominator we have 1 by 4 pi epsilon naught. In discussion of the dielectrics, let's once and for all settle down this epsilon naught. This is the dielectric or the permittivity of the free space, right? So epsilon naught is nothing but the permittivity of free space, and the r to the power 5, note this r to the power 5 in this expression, and r is the magnitude of the distance, right? So we know what is the electric field at some point away from this dipole. So these things will be useful in lectures to come. And then another question I want to ask here is that what is there are many differences between an good conductor and an insulator, right? So what are the good conductors? Let's say we have copper, right? So copper is the metal, and it really is a good conductor of electricity. But what is a fundamental difference in terms of the electric field behavior between an insulator and a conductor? That's really an important point to remember. So here I'm trying to discuss that for a perfect conductor, right? By that I mean the perfect conductor means it must have an infinite conductivity, right? So let's say the resistivity of this material should be 0, right? That's a perfect conductor. And the idea is that for a perfect conductor, the electric field inside the perfect conductor is always 0. That's a really important thing to remember, that a conductor, if we apply some electric field, the electric field inside the body of the conductor will be 0, right? And the way it happens is that, let's say we have some piece of conductor, right, and we are applying an external electric field in this direction, right? That this is E external, so these are all vectors, right? And what will happen, this is a static electric field. What will happen is that the charges, right? So this is a metal. So what is special about metals? That they have lots of free electrons, right? So that's a characteristics of metal, that they have enormous number of free electrons. So these free electrons can really move, right, inside. They are very mobile. They are very mobile inside the material. So when you apply this static electric field, electrons will pile up in this edge, right? Because they can move and they can quickly will be along the surface of the material in this side, because they are experiencing a force. The electric field is this side, you know, the force on due to electric field is this equation. So the electric field and the force is in opposite direction because of the charges are negative, right? So they will kind of line up here, and then they will induce the positive charge in this surface, right? And this is a positive charge induced under the electric field, and what happens really, the charges start moving, and they kind of keep moving until the distribution inside the material is such that due to these charges, you can see the electric field will be created, which is the EI, or internal electric field inside the metal. Charges will keep moving, like the electrons will keep moving on this side, piling up some positive potential on this surface, until the electric field inside the material exactly cancel the electric field, the external electric field, right? And that's what happens. So we have a pile up charge in the surface, we have some pile up charges in the surface, but inside the body of the conductor, the electric field is identically 0. So what is the significance? Let's say we have some atom here, right, of that material. The electric field felt on the atom will be 0. So inside the conductor, the local field, individual local field on atoms, the atoms do not feel any electric field, right? Because the atoms are inside the conductor. That's a fundamental thing you should remember, that the electric field inside the conductor is 0. Another thing to ask is that how the electron, right, knows that when to stop, right? Because they were moving, and they will make a charge distribution inside in the surface of the metal in such a way that the charges, the electric field produced exactly cancel the electric field, externally applied electric field, right? And the answer is that they will stop when the two electric field cancels each other, right? That's a equilibrium charge configuration for the metals. But the distinction is that for insulator, right, charges cannot flow, right? If we apply some electric field, the charges cannot be, there is no free electrons, right, and then they cannot really flow, and that's why they really cannot cancel the electric field applied externally, right? So the electric fields will penetrate into the insulator, right? And that's the fundamental difference between an insulator and the metal, that the electric field will penetrate inside the dielectric or insulating material, and what will this electric field will readjust the electrons and ions in that insulating material. That's the key to remember, that this is why we make a separate discussion for insulating materials, because the difference is that the electric field will exert some force on individual atoms, ions, or whatever you have inside the insulating material, and they have some charges. Those charges will be redistribute themselves in the influence of external magnetic field, right? So to explain that, let's say we have some atom, maybe there is a big piece of insulator, and then I'm just focusing on a single atom, right? And in single atom, the plus, this white region is like the nucleus, right? That's a positive nucleus, and what we have in the nucleus is protons and the neutrons, which are much heavier than the electrons, right? That's one thing to remember, because you know, the electrons are like 1800 times lighter than the protons, right? So the nucleus is really heavy, and the electrons, and this is the electronic distribution, right? These clouds of electron. And you can see this is like a spherical distribution, so the center of gravity or center of mass for all this charge distribution is exactly this spherical positive charge distribution, which is here, right? So the center of positive charge of the ions and center of the negative charges of ions are exactly on top of each other, right? So as a whole, you don't there is a charge neutrality condition is maintained, because the center of gravity or center of mass of negative and positive charges are on the same side. But let's say now on this atom, let's say we are applying some external electric field in the material, and due to the insulating behavior, the electric field will penetrate inside the material and it will experience the forces on the charges, right? So now let's say the electric field we are applying in this direction, and you can see the clouds of electron will experience a force opposite to the electric field, right? That's why this spherical charge is kind of distorted, and you will see like elliptical shape, right? And the positive charge will feel force in the direction of the electric field, right? That's the direction of the force for positive nucleus, and this is the force for the negative electrons, and they're kind of opposite in direction. But one thing to note is that due to the heavy nature of the nucleus, the displacement of the nucleus will be very small compared to the displacement of the electron, because electrons are much lighter. That's why they will be distorted, right? And what happens is that now let's say somewhere here we have another set of pictures somewhere here. I will explain it later, but the center of negative charges are not on top of the plus now, because the charges are kind of distorted. So we have some minus center of gravity for the minus charges. So it is as though we have a dipole here, right? Some plus charge and some minus charge, and that's separated by some, let's say, some distance x. So you can see it is as though we have a dipole in the presence of some external electric field. And to make this argument much clearer, I have a set of picture where I'm showing that the center of gravity for the positive and negative charges are same when the electric field is 0. Now we are applying some electric field, the positive charge will shift towards the electric field, and the negative center of gravity will be distorted, and the shape will be a bit distorted, right, of the spherical symmetry. And then the important thing to understand is that this positive center and the negative center behaves as a dipole, right? And they have some equilibrium position, let's say, under the presence of electric field. And the important thing that we model this dipole that's connected with a spring, right? And let's say we have some spring and mass problem. So this positive and negative center mass have some mass to let's say maybe some m, right, in our model, right? So we are thinking about that some charges are separated by some distance d, and they are connected with some spring, right? So let's say spring constant is K. The important thing to remember this sort of spring mass problem is that they always have some vibration resonance frequency, right? The characteristic frequency at which this spring wants to vibrate. And from your undergrad physics courses, you know the frequency of vibration for this sort of spring mass system is nothing but 1 over 2s pi root over k by m, right? So the frequency of vibration, natural frequency of vibration of this spring depends on the mass that's connected the spring and also the spring constant, right? So the stiffer the spring, changes the frequency of resonance. If the masses connected with the spring are different, it will also change the resonance frequency, right? And these things will become important because when we discuss in the lectures to come, you will see that this frequency of vibration for the dipoles inside the material has to be comparable to the externally applied electric field fluctuation. So there are some relation between this spring constant, mass of the dipoles, stuff like that, right? Okay, but the key point is that electric field penetrates inside the insulator. The electric field exerts some forces on ions and atoms. It kind of distorts the readjusts the charge distribution and forms a dipole, right? It's induced dipole. That's the key word. Inside the insulator material, under the influence of electric field, dipoles are induced. Okay, and then the last thing that I want to introduce here is that this concept of uniformly polarized, so it should be an R there. So uniformly polarized sphere. These things we will be using in some lectures where we will estimate the electric field in some insulating material. So we need these formulas from our discussion of electromagnetics. And the idea is that let's say we have some sphere, and the sphere is of radius r, and let's say this is the direction of z, and we are saying is that the sphere is uniformly polarized. It means we have some plus charges on the surface and we have some negative charges on this surface, right? And the charge distribution is uniform. That's why it's a uniformly polarized sphere. And this distribution sometimes can be understood by displaced. You can see there is one sphere here and there is another sphere here. So it's kind of a two displaced sphere, and we have some positive charges here and some negative charges in this side, and they will create some dipole moments, right? So as soon as we have some charge separation, we have some dipole moments, and we have already discussed this dipole moment is always from the minus charge to the positive charge, right? And the question to ask is that if we have some charge distribution where a sphere is uniformly polarized in this fashion, what is the electric field inside the sphere, right? And the idea of the formula to use is that the electric field anywhere inside the sphere is uniform, so they have the same value, and the formula is that E is equal to minus P is the polarization, 3 epsilon naught, and this is the permittivity of the free space, right? This is an important formula that will be useful, we will see in lectures to come, right? So for a uniformly polarized sphere, the electric field inside that sphere is minus P by 3 epsilon naught. And you can find out these discussions in any standard electromagnetics textbook, right? Like from one before I'm using from Sadikhu. So Alexander Sadikhu, you can have a look there. These are really very standard derivations, and we'll be using this formula in some lectures in the future, right? And I think for this lecture, that's about it, and thanks for listening.